So far, you may have noticed that sometimes when evaluating the limit of a function at a, the result is the same as simply finding the y value at a. That is, what's happening near a is sometimes the same as what's happening at a. This happens when a function is continuous at a. Functions like this are very convenient because it's much easier to simply evaluate a function by substituting it in than it is to evaluate a limit, making a table of values, looking at what's happening near the graph, or using limit laws. So let's look at a definition. Continuity. A function f is continuous at a if the limit as x approaches a of f of x is f of a. So again, this is saying as what's happening near a is the same as what happens at a. A function is discontinuous at a if the limit as x approaches a of f of x does not equal f of a. So let's look at some examples of this. And also visually, if you think about this, what's happening is a function is continuous if you can actually sketch the graph and you don't have to lift your pencil. So if I looked here at f of x, I could see that this is continuous. I can sketch this entire graph without lifting my pencil. So here we would say this is continuous. If I looked at this function g, we could see here, we could use the definition and see that what's happening, this limit as we're approaching 1 is not equal to the value of the function at 1. So as we're approaching 1, we're at 2. The value of the function at 1 is -2. So we could say this is discontinuous at 1. You can also just see visually, if you have that graph, if I go to graph this, I'd have to lift my pencil up here and then go back. So whenever you're having to lift that pencil up, it is discontinuous there. So this is discontinuous at x equals 1. Okay, let's look at this one. So here we have a graph that is going towards an asymptote. So this x equals 1 is a vertical asymptote. So we can see if I'm approaching 1 from the left and right, we're going towards positive infinity. That's not an actual value. There is no f of 1. So f of 1 does not exist here. Again, if I were to graph it, I'd have to lift my pencil up when I get to x equals 1. So this is discontinuous at x equals 1. And then the last example I have is when we have something that looks like this. So again, if I were to graph this, I'm fine until I hit x equals 1, and then I have a problem and have to lift up my pencil. So this is discontinuous at x equals 1. So these are all different types of continuities and discontinuities. So we're going to actually define these pretty soon. Let's look at these 4 graphs more closely to explore different types of discontinuities. Notice the function h isn't all that bad, even at x equals 1. That is, if we approach x equals 1 from the right, the resulting right-hand limit is the same as the function value. So again, if you're approaching 1 from the right, that's going to give us -2, and the function evaluated at f of 1 is -2, so those are the same. So this leads us into the terms of directional continuity. So a function f is continuous from the right at a if the limit as x approaches a from the right is equivalent to f of a. Conversely, it's continuous from the left as you're approaching the limit from the left-hand side, should be a minus sign there, is equivalent also to f of a. So let's look at this and define some other types of continuities. So looking at this first function f of x, again, we've said this is continuous, always. If I look at h of x, we would say, this is where this directional continuity comes into play. So we'd say this is continuous from, it is right continuous at 1. Okay, so, and that's because the limit as x approaches 1 from the right-hand side of the function equals what the function's value is there. So this is still, the function is discontinuous at x equals 1. So it's still, we say it's discontinuous, But we can then specifically say it's continuous from the right at x equals 1. Does that make sense, hopefully? So again, this function is still discontinuous at x equals 1, like we said on the other slide, okay? This type of discontinuity, this is called, so again, this is still discontinuous at x equals 1. This type of discontinuity is called a jump discontinuity. Think about why. If you look at it, you go from here and then we're jumping down to get to that one there. If we look at g of x, this is called, so remember we said this is discontinuous. I can't spell. At x equals 1. This is not continuous from the left or from the right because neither from the left or the right do we equal what the function's value actually is, like we did in h. So this is discontinuous at x equals 1, and this is called a removable discontinuity. Okay? So this is just a point that was basically removed is how I kind of think about that and remember that. For j of x, again, we said this is discontinuous at x equals 1. And this is called an infinite discontinuity because it's going towards infinity. We have a vertical asymptote there. Continuity. There we go. All right. So let's look at more. So given the graph shown, determine the values of x for which the function is discontinuous. Additionally, state the type and whether it is left continuous or it is right continuous. So here we can see I'm going to have an issue. So again, where you're going to be lifting up that pencil at x equals -4. So it's discontinuous at x equals -4. The type of discontinuity there, it's a jump because you jump from here to there. So it is a jump discontinuity. And let's see, is it left continuous, right continuous, or neither? So here, as we're approaching -4 from the left, it actually equals what the function is at -4. So the limit as I'm approaching it from the left-hand side is 3. The function is 3 at f of 4 because there's that closed circle there. So we'd say that this is left continuous. Okay, now let's see, where else are we going to run into some problems? So as I'm going up here, there's a point there, but it's a solid circle, so that means it is fine there. So I don't have to lift up my pencil, but I'm going to get to here and I'm going to have to lift up my pencil again. Dang it. So at x equals 2, we have another discontinuity that is also going to be a jump discontinuity because you'd have to jump to get to that one. And again, we'd say, because as I'm approaching this value from the left, so as I'm approaching 2 from the left, the limit is -1, and f of 2, so the function at 2 is -1, so this is also left continuous. All right, and then looking at the next time I'd have to lift up my pencil would be right here at f of 4, so x equals 4. This is called a removable discontinuity. So let's see, so as I'm approaching it from the left, the limit's approaching 2, from the right it's approaching 2, but f of 2 is undefined, so this is neither left nor right continuous. Okay, let's look at another example. So let's draw this graph, so it looks like I'm good. I don't have to lift up my pencil until, right there at x equals 2, or -2. So at x equals -2, I have discontinuity. And that is a removable. Again, the limit as we're approaching it from the left is 3, as I'm approaching it from the right is 3, but the function is 5. So the limit as I approach it from the left and the right do not equal what the function is at -2, so this is neither left or right. Okay, now let's keep on drawing this graph. I'm going to come into an issue where I have to lift up my pencil again right here at x equals 1. This is going to be a jump because jump to get back into this spot here. So this is a jump discontinuity. And this is also neither because as I approach it from the left, the function's approaching -3. From the right, the function's approaching 4. But f of 1 is 2. Neither of those are equal, so this is neither. And then going down to 4 is when I'm going to run into my issues because we've got a vertical asymptote there. So at x equals 4, there's a problem where this is going to be an infinite discontinuity. And again, this is neither because f of 4 is not even defined.